In this video, we solve problem 8.3.13-T from Essentials of Statistics, 6th edition by Mario Triola. The problem statement says a data set includes data from student evaluations of courses. The summary statistics are n equals 94, x bar equals 3.85, s equals 0.57. So we've got sample size, we've got the sample mean, and we've got the sample standard deviation. We're asked to use a 0.05 significance level to test the claim that the population of student course evaluations has a mean equal to 4.00. We're asked to assume that a simple random sample has been selected and identify the null and alternative hypotheses, the test statistic, the p-value, and then state a final conclusion that addresses the original claim. Now, because we're asked for the p-value, we're going to have to use technology, and I will show you how to find that p-value using Excel, but I also want to show you how to solve this problem or similar problems without technology. So let's say you're taking an exam and you don't have access to Excel to compute the p-value. In that case, it would be most appropriate to use the critical value method as opposed to the p-value method to test the claim about this mean. So that's the plan. We're going to do this two ways. We're going to test the claim in two ways. Once using the p-value method, because we are asked for the p-value in our homework assignment, but then we're also going to use the critical value method because that is the method that we would be using on an exam because we're not going to have access to Excel during an exam. Now, if you have a TI 83 or 84 plus and you've been learning to use that to come up with p-values and other test statistics, you are welcome to do that on our exam. But that calculator is not required for our course. So if you don't have the expensive calculator, you can just use the critical value method as we will do in this video. Okay, so we always start a hypothesis test by stating the claim and then stating what would be true if the claim were not true or if the claim isn't true. Let's see, it says we want to test the claim that the population of student course evaluations has a mean equal to 4.00. Since that contains the condition of equality and it isn't just a pure equal sign, it's not even a less than or equal to or greater than or equal to, turns out that the claim is the null hypothesis. If that's not true, we would have the mean is not equal to 4.00. So we see that. Now, since that is a not equal to sign, that means we have a two-tailed test. We don't care if the mean is higher than 4 or lower than 4, if it's not equal to 4. If we have evidence that suggests that the mean is not equal to 4, we're happy. Or not happy, but you know what I mean. In that case, then we would reject the null. Okay. So let's go to our homework assignment and choose the correct null and alternative hypotheses. Looks like option B is the one that we're looking for. Great. And next we want to determine the test statistic. I'll share my paper with you. Okay, so if we want to compute the test statistic, remember what that is. That is the t-score in the case when the population standard deviation is not known. That's the t-score corresponding to that value of x bar in the sampling distribution of the sample means. So we're thinking of creating a bunch of samples, all of size n equals 94, and every time we collect 94 student evaluations at simple random sample, we compute a mean from that student evaluation or from that sample of student evaluations. And we do that over and over again for all the different samples. And then we look at the distribution of the sample means, and it's going to look something like this. Now, back in lesson 6.3, we said that the mean of the sample means is equal to the true population mean because that sample mean is an unbiased estimator of the population mean. Now, whenever we're doing a hypothesis test, remember, we're always assuming that the null hypothesis is true. So we're saying to ourselves, if the null hypothesis is true, is this x bar equals 3.85 significantly low? I'm saying significantly low because it's below that mean equal to 4.00. Now, since we're doing a two-tailed test, we don't even care if it's significantly low or significantly high. We just want to know, is X bar significantly different from this mean that is given um, in our null hypothesis? The way we determine if X bar is significantly different is we convert from X bar to a t-score using this formula. It's a lot like computing a z-score, but your random variable is X bar. So we've got X bar, we're going to subtract the mean of the X bars, and then we're going to divide by the sample standard deviation associated with the X bars. So we'll have, well, actually, this is given by the mean assumed in our null hypothesis. And down here, we're going to have the sample standard deviation divided by the square root of the sample size. So in our case, X bar was 3.85. The mean that, or the mean population mean, excuse me, that we're assuming whenever we do the hypothesis test is the mean given in the null hypothesis. So we're subtracting 4 and we're dividing by the sample size, which is 0.57, and we're dividing that by the square root, or I said sample size, that's 0.57 is the sample standard deviation. And then down here, we're dividing by the square root of the sample size, and the sample size happens to be 94. If we do this computation, that's going to get us the value for t. So I'll do the numerator first. Divided by, open parentheses, 0.57 divided by square root of 94. Get out of that radical, close the parentheses for the denominator, hit equals. And sorry about the reflection there. We get about negative 2.55. So that is not a number of standard deviations below the mean, but it's something like that because standard deviation over here is not equal to 1. But we're saying, okay, if you have a t-score of, or a test statistic t of t equals negative 2.55, we're saying to ourselves, is that significantly different from t equals 0? Which is the same as saying, is this X bar equals 3.85 significantly different from this mean of 4? If it is significantly different, then we're going to say, well, if that is so uncommon, but it's actually happening, then maybe the assumption that led us to believe it was supposed to be uncommon is false, it's incorrect, so we'll reject the null hypothesis if this is significantly different from that. And the area in this tail and the area in this tail are supposed to be the same. I just didn't do a very good job drawing my picture. So let's go back to MyLab statistics and enter our answers over there. Oops, sorry about that. Okay, and they wanted us to round to 2 decimal places. We have negative 2.55. Okay, great. And then we're asked to find the p-value. Now the p-value is associated with this test statistic, and it's also associated with that X bar. P is the probability of getting an X bar that is as extreme as our X bar or more extreme than that. And since we are talking about a two-tailed test, we're not just saying a p-value, or is p is the probability that X is equal to 3.85 or less than 3.85. We also want to say on the other side where the corresponding X bar is, if this was symmetric, if I'd done a better job with my picture. You know, that these X bars are significantly different from the mean too, in exactly the same way. If this distance from here to here is equal to that distance from there to there, and say, okay, or alternatively, like this area and this area is the same as like this area. If this is my test statistic t, and this is another t equals 2.55 that's positive, I'm saying what is the probability that t is equal to negative 2.55 or less than that, or t is equal to positive 2.55 or greater than that. So what's the probability that t is equal to this value or more extreme than that value? That's our p-value. And we can use technology to find that. So we can say that this is the probability that X is, or X bar is less than 3.85, but then we double it because it's a two-tailed test. Or we can say this is 2 times the probability that our test statistic t is less than approximately negative 2.55. And you've got two options in Excel for this. You can use t.dist.2t for two tails, and then you'll just enter the test statistic and the number of degrees of freedom that are associated with a student t-distribution. If n is equal to 94, the number of degrees of freedom is one less than that. So that's going to be 93. Or we could do 2 times this t.dist function, which is going to give us the area to the left of this. So we'll say negative 2.55. They're going to want the degrees of freedom, and then they're going to ask if you want a cumulative distribution. So they're just saying, do you want all the area to the left? And we're going to say yes. So we'll say true. If you use either one of those, you're going to get the right answer for our p-value. Let's do that now. So we type equals t.dist.two tails, 2t for two tails, and then we'll enter that t-score, negative 2.55 approximately. And we've got 93 as our number of degrees of freedom. It's not liking that. Maybe I didn't enter it correctly. T is negative 2.55 and the degrees of freedom are 93. Huh. I don't know why it's not liking that today. It worked just fine yesterday. How about t.dist? Negative 2.55, 93, and true. Okay, so I guess that one is working just fine. I don't know what's wrong with the other one. Yeah, I have no idea why that two-tailed one isn't working. Let's see, what does this error message say? Help on this error. Okay, something was happening with the iteration. Okay, well, it doesn't matter. We can still use t.dist, and that's giving us the area to the left, but we want to double it. So I want 2 times that area to the left, which gives me this. And I think they want us to round our error or round our p-value to 3 decimal places. So I have 0.0124. Okay, so if we round to 3 decimal places, that's 0.012. Okay, now we want to state the final conclusion that addresses the original claim, and that comes from comparing this p-value to our alpha value. Let's see. Our significance level is 0.05. It's stated right up here. And the p-value is less than 0.05. So that means we're going to reject the null hypothesis. And since the original claim was the null hypothesis, and I was going to say it's equal to the null hypothesis, but the claim is the null hypothesis, we're going to say that there's sufficient evidence to conclude that the claim is incorrect. So there's sufficient evidence to conclude that the claim is not correct. Okay, so that is how we do that using the p-value method. I want to show you how to use the critical value method as well, because that's probably what you'll have to use on an exam when you don't have access to something like Excel to do your calculations of the p-value. So in order to do that, I'll share my paper with you. Okay, so with the p-value method, we saw that we ended up rejecting the null. So we end up saying that there is sufficient evidence to conclude that the null hypothesis, which happens to be our claim, isn't true. we're going to get exactly the same result if we use the critical value method. And the critical value method is done in pretty much the same way. You've got to do all of this in the same way that you did before. So you need to identify the claim, use the claim to infer the alternative and null hypotheses. Then it's a good idea to draw that sampling distribution of X bar and think about how that corresponds to the student t distribution. Then because we were asked to find p-values, once we found then we had to find the test statistic. And this computation got us the test statistic. So that's the t-score that corresponds to this X bar from our sample. Now the question is, okay, from here, we could use Excel to find the corresponding p-value, but what if we can't? What if we don't have Excel with us? All we have is table A2, Triola Formulas and Tables, or not table A2, but the Triola Formulas and Tables to infer, whether we should reject or fail to reject the null. So in this case, then we would use the table of critical values of t in those formulas and tables. So let me show that to you. Okay, so this is page 7 of the Triola Formulas and Tables that we use in our course. And this is giving you critical values of t. Now, not all of the possible degrees of freedom are listed here. Our degrees of freedom are 93. So I would go over here to this leftmost column and I'd look for 93. Now, if we don't have 93, we always round down rather than rounding up. That's just going to be lead to more conservative estimates. So we're going to round down to 90 for degrees of freedom. And we have to think about whether we have a one-tailed test or a two-tailed test. Remember, this was a not equal to sign, so we had a two-tailed test. And our alpha value was 0.05. That was our significance level. So when you have a two-tailed test and your alpha equals 0.05, what you want is an area of 0.05 in two tails. So we go up to the top here, and you want an area in two tails of 0.05. That's that middle column. And that's going to give us the critical t value associated with 90 degrees of freedom. So that's the critical t value right there. T equals plus or minus 1.987. Okay, now 1.987 is going to be closer to the middle here than this negative 2.55 and the positive 2.55. So this corresponds to T critical equals negative 1.987. And this one corresponds to T critical equals positive 1.987. And the area beyond these guys, now this is not to scale, that blue area is equal to alpha. So if we aren't able to compute this p-value so that we can compare this red area to this blue area, rather than comparing the red area and the blue area, comparing that alpha to the p and using that to say the red area is less than the blue area, so p is less than alpha, therefore we are going to reject the null hypothesis. Instead of doing that, what we can do is we can compare the critical values of t to our test statistic t. And so we'll say that since this critical or this test statistic t is in our critical region, this blue region is called the critical region. That means the test statistic is significantly high, and therefore we're going to reject the null hypothesis. Now, another way of saying that is to say this. Let's compare the absolute value of our test statistic to the absolute value of that critical value. Well, since the absolute value of the test statistic is greater than the absolute value of the critical value, that means that test statistic is farther out in the tails than the critical values are. And that means that the test statistic is in the critical region. So if this is true, we're going to say that that test statistic is significantly high. So or significantly, absolute value of the test statistic is significantly high, significantly different from t equals 0. So we're going to reject the null hypothesis. So you can compare the test statistic and the critical value like this, just using that inequality. I don't recommend this method though, because for some students, it feels like memorization. And it also feels like you're like, which one goes on which side again? What I would rather you do is that you look up the critical values of t, and then you sketch a student t distribution that looks like this, and then draw that or sketch in that critical region in a certain color, and then look at your test statistic t and graph it relative to the critical region. If t test is in the critical region, so it's farther out in the tails than those critical values of t, then we're going to reject the null hypothesis. If t test is in between those critical values of t, we're going to say, well, that value of the test statistic is likely to occur due to chance. It could easily have occurred due to chance if the null hypothesis is true, and therefore we won't reject the null. So if the t test is out here, reject the null. If the t test is in here, fail to reject the null. And that's how you do it without the technology. But notice that comparing the test statistics to the critical values and comparing the red area and the blue area are going to get you exactly the same answer. You're going to end up rejecting the null either way. I hope that helps.